Hey guys, welcome to our first step on our adventure with the binomial expansion. So in this one, we're going to meet something awesome called Pascal's triangle, which comes from the binomial expansions of 1 plus x to the power of n. So we're actually going to be doing some binomial expansions, although they are the very, very basic ones. So, first up then, expanding 1 plus x to the power of n. So, we're going to start here with 1 plus x to the power of 0. Now, anything that we set to the power of 0 is just going to give us 1. So that right there is the nicest binomial expansion you will ever see. Let's go up 1 power. Let's expand 1 plus x to the power of 1. Now, anything set to the power of 1 is just that thing itself. So that's just going to give us 1 plus. Now, we're going to do something a bit weird here. Even though we've only got a single x, I'm going to write 1x. So we got 1 plus 1x. Step it up by 1 power again. So let's go to 1 plus x to the power of 2. Now that, we can all do that happily. That's just a double bracket expansion. 1 plus x times 1 plus x. So if we do that, we would get 1 plus 2x plus 1 x squared. Let's go up another power. So let's go to 1 plus x to the power of 3. Now we could do that. That's a triple bracket expansion. 1 plus x times 1 plus x times 1 plus x. We were doing things like that at GCSE. So we could do this. What we would get is 1 plus 3x plus 3x squared plus 1 x cubed, like that. Let's step it up another power. So let's do 1 plus x to the power of 4. Now, as the power is getting bigger, this is starting to become more and more of a pain in the ass. We could do this. This would be 1 plus x times 1 plus x times 1 plus x times 1 plus x. Now that, as I said, we could do it, but the whole point of this chapter is to do things like this in a more clever, quick way. Now I'm just going to tell you that that would give us 1 plus 4x plus 6x squared plus 4x cubed plus 1x to the power of 4. So, something that we can notice here with these expansions, whatever the power is, there is always one more term in the expansion. So when we had a power of 0, there was 1 term. When we had a power of 2, there were 3 terms. When we had a power of 4, there are 5 terms. Now what we're going to do, before we do any bigger expansions, we're going to take the coefficients of each expansion and arrange them in a triangle. Because we've got a little pattern going on here, and there was this French dude called Blaise Pascal that spotted this pattern and made this triangle that we're about to see. So, for you, make a note of these expansions, and then on the next page, we're just going to be dealing with the coefficients. So, the first one was just a 1. Then we had 1 and 1. So we had 1 plus 1x. Then we had 1 plus 2x and then 1x squared. And then we had 1 and 3x, and then 3x squared, and then 1x cubed. So I'm going to stop there before I fill in the next row and show you the pattern that's going on. So we start off at the top, 1, 1, 1, nothing really very exciting is going on there. But then though, when we move down, this 2 comes from adding the 2 1s up above. So 1 plus 1 is 2. Now we always start with the 1s on either end of the rows. So that if we go down, we start off with the 1 on the outside, and then this first 3 comes from adding 1 and 2. So that's where we get 3. And then the second 3 comes from adding 2 and 1. So again we get 3. So that's how I knew the expansion of 1 plus x to the power of 4, or it's how I knew the coefficients. It's from this triangle. So we start with a 1 on the left hand side, then 1 plus 3, which is 4, then 3 plus 3, which is 6, then 3 plus 1, which is 4, and then on the end we've got a 1 again. So we could then find the coefficients of expansions to the power of 5. Now when we get to a binomial expansion to the power of 5, that's really when we definitely don't want to be doing it by expanding the brackets. But Pascal's triangle makes it so simple. So we're going to start with a 1, and then 1 plus 4, which is 5, 4 plus 6, which is 10, 6 plus 4, which is 10, 4 plus 1, 5, and then we've got just the 1 on the end. So this is how our triangle is looking at the moment. Now, a few things to notice here. I'm going to call this top guy, I'm going to call it the 0th row, which always sounds a bit mental to call something the 0th, but it is. The second row is the first row, the third row is actually the second row, and then etc, etc. So then we've got our third row, and our fourth row, and then our fifth row. So, okay, up to you then. So we're going to be seeing these coefficients a lot. We need these coefficients no matter what expansion we are doing. So it's not just when we are expanding 1 plus x. We need these for any binomial expansion that we are going to find in year 1. So another thing that's important to realise, whatever power you are expanding to, you then need the coefficients from that row of Pascal's triangle. So when we were expanding to the power of 3, for example, we would need the coefficients from the third row. So we would need these guys, 1, 3, 3, 1, for any expansion to the power of 3. So if we were expanding to the power of 4, then we would need the coefficients 1, 4, 6, 4 and 1. If we were expanding to the power of 5, well, we would then need 1, 5, 10, 10, 5 and 1. Now there's another thing here that we can notice. The triangle is symmetrical down the middle. So notice on the even rows, we get, it builds up to the middle number, and then it goes back down symmetrically. So with the power of 2, we get 1, 2, 1. With the power of 4, we get 1, 4, 6, 4, 1. Now when we have odd powers, we don't get a middle value, we get 2 of the same values in the middle. So we're the power of 3, 1, 3, 3, 1. With to the power of 5, 1, 5, 10, 10, 5, 1. So that's another thing to look out for. So let's use Pascal's triangle to do the expansion of 1 plus x to the power of 7. So up to now then, with Pascal, we've got powers up to our 5th row. So for the expansion to the power of 7, we are going to need the coefficients in the 7th row. So we need to build up our triangle a little bit more. Okay, sorry for the jump, had to move my triangle. So let's find the 6th row first of all. So we'd have 1, and then 1 plus 5 is 6, 5 plus 10, 15, 10 plus 10, 20. Now we're in an even row, so our coefficients are symmetrical. So we built up to 20, we're now going to go back. So 15, 6, and 1. So that's our 6th row of coefficients. So we can now get our 7th. So we're going to have 1. So let's fill this in as we go. So our expansion is going to have 1. Then we got 1 plus 6, 7. So we're going to have 7x. And then 6 add 15 is 21. So we're going to have plus 21 x squared. Then we're going to have 15 plus 20, which is 35. So we're going to have 35x cubed. And then again now we've reached the middle. So 20 add 15 again. It's 35. So we got 35x to the power of 4. And then we've got 15 add 6, which is 21. So we got 21x to the 5. And then we've got 6 add 1, which is 7. So we got 7x to the 6. And then finally, we're going to have our 1 at the end. So there's our 7th row. And that's going to give us then our final term, x to the power of 7. So, what we can tell from that then, Pascal's triangle is completely magical, but as our powers get higher, it's going to get a little bit more annoying to have to write out the triangle. So it's fine for small powers. Luckily, there is a trick or a formula that we can use for bigger powers, which we're going to see very, very soon. So, hope you found that useful. See you in the next one, guys.